Welcome to my talk. My name is Olaoluwa Osuntokun. I'm co-founder and CTO of Lightning Labs, working on Bitcoin for, I guess, maybe 8 or so years. Something like 9, Lightning for like 7 or so of those as well too. Working on some new things called Taro, get into a little bit later in the talk as well, right? So the title of my talk is basically starts on Bitcoin, right? So kind of like exactly what it looks like to actually get started on Bitcoin itself. How do we do it? What's the kind of path to gain mindshare? How do we actually develop the technology itself to actually get it on the OG blockchain itself, and also maybe even where a lot of these stuff was actually hypothesized in the first place, right? Because remember Eli's talk in the beginning. He talked about kind of like his talk in 2013 or so, which was actually at a Bitcoin conference, and now this kind of full circle back to how do you actually get this back to where what was kind of like inspired by individuals to get things going. So first, talk about why Starks in Bitcoin. Kind of like why do we think is a good idea itself? So what I'll kind of describe what I talk as far as kind of like a multi-pronged kind of like ecosystem integration approach as far as getting mindshare and kind of like getting maturation in the technology. First talk about kind of like the Starks application of the Bitcoin P2P network itself, kind of like things like instant sync and also kind of like black header sync, like clients on the full nodes as well. So I'll introduce something called Taro. So this new thing we're working on at Lightning Labs, kind of like basically a way to like represent assets on top of Bitcoin, and also actually even send them on top of the Lightning network as well to work on assets and collectibles. And then I'll talk about ZK Taro is kind of like the bigger thing at the end of the talk as far as like integration Starks into Taro itself as a way to actually get sort of like more packages in Starks itself, and also kind of like have like a sort of like a soft fork dry run with the way that Taro works. And I'll get into that a little bit later. So first, why Starks on Bitcoin, right? I probably don't even really need to explain, to y'all kind of like benefits, but obviously, privacy, because today you have like the entire graph is fully public, right? You basically have all the values, you have all the input, the transaction graph as well too, and that's not really that great of a thing, right? There's something called confidential transactions, which is deployed into something like Liquid, but that only really gives you the input and output value amounts that are hidden, right? You don't really actually get the entire transactional graph because at that point you basically still have a lot of what's going on. You can see who's sending to who, but you don't necessarily see things like the value themselves, right? Which still a lot of things actually being leaked out. You also get information like compressing the transaction graph as well, because now on this point you don't necessarily need to basically import the entire thing. You can have like a sort of like a snapshot of the transaction graph itself, which obviously is really good. One of the big things is obviously scalability, right? So one of the great things about Starks is you basically have this sort of like amortization as far as getting more bytes, getting more transactions in a given byte, right? If it can have maybe the proof is like 200 to 200 kilobytes or so, but that's maybe like a million transactions together. That's obviously a big thing, right? That's always like the main motivation of like the Lightning network itself, as far as doing something like off chain to actually get more transactions with a given byte. I can have a channel open maybe it's been open for 3 or 4 years. Maybe I've done thousands of transactions in that, but then closing on chain and really knows about that, right? Obviously, the big thing there is kind of logarithm scaling as far as having savings on terms of like batching, which is obviously good for scalability, efficiency, utilization, and so forth, things like that as well too. And I think one other thing I remember in the past when things like Starks come up, people were like, okay, well, these very very large things on chain, can we actually handle that on the Bitcoin blockchain network itself? I think one thing most people don't realize, most Bitcoin transactions are actually somewhat large now, particularly when you have things like multi-sig, you have like TabScript, you have things that are doing things like merging multiple inputs. For example, if you click on this one, I probably should have TXID. This the Bitcoin transaction has like 200 inputs, which basically just something like consolidation. It's actually 65 kilobytes, right? Which is like somewhat big, right? I think in the past we'd be like, oh, Bitcoin transactions like 200, 300 bytes, but like not anymore. So you actually have like a lot more things on chain. But the main thing is, okay, well, can we use those 65 kilobytes to basically have like more and more transactions in the chain itself? Can we actually impact these things and get more scalability that way as well? And obviously one thing as well is basically transparency, right? And one thing is in the past, like things like Starks came out back in the day, and people were like, oh my god, the CRS, or I guess what they call it SRS now, that's trusted setup, right? That's basically like a bad word in the current land, right? But obviously Starks are great because you have that transparency, and so you don't actually need the trusted setup capability itself. And I think there are a lot more kind of understandable and other things like some of the pairing-based protocols that get a little bit more in the Moon Matthew territory and so forth. So that's kind of like motivation as far as why do this stuff in the first place. And so, I've been thinking about this for a bit of time in terms of why exactly have we not really seen that much activity among Bitcoin developers in the space itself, right? I think part of it is a little bit kind of like, them not really maybe keeping up with kind of like the maturation of things like, tangible technologies like, like Taro and Starks and things like that as well too. I think the other part of it is that maybe they aren't really sure if things are ready or not yet. Maybe they have kind of like a mental model that maybe it's from the past 7 years or so, but they haven't really keeping up with a lot of the, new changes, right? So the question is okay, do we think it's ready right now, right? So basically go into Bitcoin, next, let's say we had, Handwave, soft forks, whatever else, we can do this right now. I would say, probably not, right? But I think that's okay. But I think the main thing is basically to allow people to keep up with a lot of the innovation, basically, so we can get more mindshare, we can get more practice, and we can also actually see exactly how these technologies can be integrated in the future itself, right? So the question is how can we do this stuff as far as building excitement and getting more practical hands-on experience in the system itself? I would say kind of go from the outside in. So basically, don't start directly at the consensus and don't start doing a soft fork to basically change the core of itself. Can we actually do things on the outside? So can we do things like the P2P network, higher layers like Lightning, things like Taro stuff that also overlay on top of the system itself, and then get more experience in these sort of Bitcoin applications to then eventually kind of like actually map onto the Stark realm in some eventual soft fork hand wave, some sort of way basically, right? But I think the main thing right now is I think there's kind of like a gap between the current maturation of the technology versus people's perception of it, and I think this talk about kind of like closing that gap and also getting people excited to actually summarize around this stuff in real life. So first, one thing is basically like lines, right? So people know like like lines of Bitcoin, you basically download the headers, and this is like objective because you can actually check out the power on the headers, and everything is great for something like that, right? And there's a really cool project called ZeroSync. If you don't know about it, definitely check it out. I'm putting on my contributor hat. Usually I'm the one making projects and directing people, but like I'm going to be a contributor to like a ZeroSync, which is really cool. And basically what they're trying to do, they're trying to actually use Stark and Taro to actually give you sort of like instant sync on the Bitcoin network itself, right? So one flavor of this is something like like client to basically download all the header state and catch up with the chain tip effectively instantly, right? And the main thing here is you're actually like you're actually verifying what's effectively like a very long hash chain, right? From Genesis all the way to this initial block, everything points back to the previous header. Previous header has collect has the correct POW, which you can verify very very quickly. It does difficulty adjustments for things like that as well too, right? And the main state function here, you basically have like the header and -1, which is the Genesis header, the next header, and they say, okay, well, applying these two together, we can then move forward to the next header itself. And this is a really cool thing because you can actually then compress the entire, you can say just like at least POW, like client verification state, something that's very very small, right? And the other cool thing about Bitcoin itself is like the headers are actually only 80 bytes or so. So all of the entire headers over the past like 10 plus years of Bitcoin, it's only 60 megabytes. It's not really that much data that needs downloaded to get things going, which is pretty cool, right? So this is something that you can do. You say, okay, well, I don't really Stark proof itself. I get like that last header and also the Genesis block, and I can start to join the P2P network and then do so immediately. But obviously, you still want to get all the power headers because you still want to do things like maybe explicit Merkle proof verification for something like that itself. This at least lets you catch the network and move forward a lot more quickly. Other cool things in this direction are something called LN channel graph bootstrap. So I'm not going to explain LN as a high level. Basically, you have this sort of like authenticated data structure, which is like the graph of all the channels in the network itself, right? And one thing people today, they always like explicitly verify, okay, well, this thing was actually in a block, and they do that either via Merkle proof, something in the future working on itself, or they maybe just have like a TX index basically look at the proof of directly within that itself. Imagine you can instead download basically like a state root of the LN graph as like presented by an individual, along with the ability to prove that every single item in the state root itself is that this valid transaction itself. And at this point, you can then go and just download the individual channels basically and the proof about their channels, along with the Merkle proof inclusion proof, or to actually download the entire blob as well, and then verify everything matches up there as well too. And there's also some other kind of like applications of things like Bit 158, which is a way you can do like clients on Bitcoin, but I'm not going to get into that right now. Another really cool application basically be a cyber instance stake, but instead for full nodes as well too. So the prior thing I just talked about is basically for light clients. And in that situation, you're only really verifying like the header proof, which is basically a POW thing, right? You're not actually verifying the validity of any of the state transitions, which is actually things spending something in the UTXO set itself. And then also the LV, every single input is actually valid as well too, right? But this is basically another type of proof that you can do. You can basically start with this chain state, get the new block, and then say, okay, then we're going to the next chain state, right? And what you see on the top right here, this is actually some code from ZeroSync. This is written in Cairo 0, and the main thing you basically have the chain state, which is obviously the block height, the POW, things like that as well too. But the cool thing is they have something called a UTXO root, right? And what UTXO is basically like a commitment over the UTXO state for Bitcoin, right? And it was designed, basically to like sort of like have some very elegant structures as far as like the way proof scale over time, things like that. But at a high level, it's basically like a forest of complete binary Merkle trees, basically, right? So rather than have one single proof, you have a bunch of these proofs together, or you have a bunch of these trees together, and you can do things as far as kind of like merging them, moving them over to basically do things like optimize for kind of the access pattern of UTXOs, which is that UTXOs typically die young, right? And one other thing that's really helpful because now like every single time you're accepting a new proof or a new state transition, you don't need to say, okay, we'll verify it, look up, in this 5 gigabyte, plus, data set, basically the next UTXO to make sure it's unspent. Instead, every single block actually has an inclusion proof into the UTXO set, basically. So it's proving that it was actually prior and unspent output, and this lets you, do things a lot more efficiently. And the cool thing about this, like let's say you basically have something approved like this, you have the next header state, then also the UTXO root, right? At that point, you can actually start validating the next block the next block as soon as it's available, because every single block will actually contain inclusion proofs into the UTXO commitment itself. You don't necessarily need the entire UTXO set, right? And the big innovation, something like UTXO, is that like, full nodes don't need to maintain the UTXO set. Once they have the root of it, and you can actually do things like whenever you verify the inclusion, you can also efficiently do a deletion from the UTXO set as well too. So now rather than like, dealing with, some like in the future 100 terabyte UTXO state, you basically trade off, bandwidth of the inclusion proofs for your own memory and thing itself, which is really cool, right? And so one other thing with this is that like, ultimately like do something like this basically, which is like, a incremental Stark proof over the entire chain history itself, actually then need something to be written more in Cairo, right? So eventually you basically need Bitcoin script itself to actually be written in Cairo, right? So the way ZeroSync works today, it's able to do it's able to do like header validity, it's able to do Merkle tree inclusion, things like transaction translation, things like that as well too. But it's really missing kind of like the actual input validation being okay, well, opt check sig verify, things like that as well too. In order to get to that realm, you actually need mostly a complete Bitcoin script implementation in Cairo, which is something that I think is definitely feasible. We've written about the language. I work on something called BCD, which is actually the Bitcoin Bitcoin implementation in Go as well too. I think that'd be a really cool project, something that hasn't really kicked off yet, but I think we'll be starting to get more activity in that area as we go. Cool. So that was just kind of like, the P2P stuff, right? So we talked about light clients, talked about, full nodes, how we can actually get things like instant sync, and also like use that itself to actually, prove out Taro, and then also get, developers more excited about things that they can do in a tangible manner, right? So I'm going to talk about something called Taro. So what's Taro? So Taro is something that we announced, I think it was Bitcoin Miami, last year or so. We're working on development right now. The next version is 0.2, which is coming out in like a month or so. But what it is, it's basically like a way to like actually represent assets on top of Bitcoin itself, right? So rather than do something like maybe people are familiar with things like counterparty, whatever else, they have like arbitraries basically. You sort of need to like scan the entire chain in order to actually know what the current state of the asset is. Instead, you basically have like a sort of like, proof provenance for every single asset itself, right? So the asset is basically a proof that, asset was created at one point in the past, basically, and every single transaction beyond that actually follow the rules of the system, properly, basically, right? So once again, you kind of like have the state transition function, you have the asset, then basically witness, and then you have a new asset, basically, you can verify that over and over again, right? So one question that comes up is like, okay, well, how do you actually have unique asset IDs in the system like Bitcoin, right? Because you don't really have like a global like, address space or contract hash, anything like that itself. But there's something called BIP34, which basically ensures that Coinbase outputs are always unique within the chain itself. So something happened, I think it was like 2011 or so, there's actually a duplicate Coinbase output. It actually overwrote, the entry in people's databases. We were like, oh, basically you need to make sure these are always unique. But you make them unique, you basically put the block height of the block header itself in the Coinbase output to make sure you actually have something that, can never repeat from the point of view of like the canonical chain itself, right? So what we do, we can basically leverage that. We have something called the genesis output, which is basically the first input in the transaction that's actually, minting, basically that's creating this new asset itself. And you basically have some other data. You have the out point, the tag, which is basically the name, the hash of the meta, which is like, that can be like a PDF or a LaTeX file, like image or something like that itself, and the output index and then asset type itself, right? And this basically lets you have like a sort of like unique asset ID within the system itself. There's some other, details around kind of like the tree structure we use. It's called like a Merkle sum of sparse Merkle tree, which basically combines the ability of a sparse Merkle tree with also Merkle sum aspects as well too, meaning that let's say I have like a bunch of leaves and I have like, five, all them, I have like 5 things of 5, that then adds up to basically 25 in the root itself. This is really cool because now you can actually validate the supply of something. I can show you that, okay, well, if I was meant to not commit to an asset any longer, I used to have 25, now I have 20. You can verify that stuff very easily. It has some other cool properties as well too. And this system also supports normal and collectible assets. Collectible assets are what people call, NFTs, but that's a really bad name. So, collectible is just much better. You're gonna have to explain the acronym of like, what you're trying to describe to somebody. And one of the really cool things about the way this works is actually very like client friendly, right? So the issue about some of these other ones, as far as like, things, the way things like op return work or whatever else in the past, is like they weren't actually like client friendly because you have to validate, you have to basically scan the chain for every single op return output because you're actually applying that to your own state machine internally, right? But with something like this, basically I say I have an asset, I give you the proof of the asset. Once again, that's explicit right now. We'll talk about how we can move that in the future. You say, okay, well, this is my asset, I can move forward, and I can, do things like that itself. And, the way it works right now, we actually also have like a scripting system within Taro itself, which is actually just another instance of the Taproot VM itself. So this is really cool because now, like, rather than like individuals needing to like learn some entirely new, application paradigm, might have different tooling or different signatures or whatever else, it basically just looks like Bitcoin. It's kind of like Bitcoin within Bitcoin, and that's some other cool properties which we can get into in a little bit as well too. And yeah, you can, do things like, verify the supply of different assets, and you can also do, kind of like, things like auctions, swaps, batch transactions as well too, because it's all in the Bitcoin application model, as we'll see in a second. All right, so I made this on like a 50-inch monitor, but it looks like they can render somewhat. So this is basically like, what Taro is, which is basically a series of like nested Merkle trees itself, right? So at the very top, you have the Bitcoin block header, which basically has the Merkle root itself. It has the Merkle transaction rate of all the transactions in the block, right? Then you basically have each of the individual transactions. One thing that Taproot did, Taproot actually added another level of a tree, which is basically a Merkleized abstract syntax tree, where you can basically have a bunch of different scripts, in the leaf, basically, and I say, okay, well, I'm going to reveal the multi-sig script or the pre-image script, some other script on like that as well too, right? So what Taro actually does is like, okay, well, we have the structure commitment structure in the place of the TapScript tree. We're going to add another commitment basically, which is the thing on the right base, which then commits to the tap tweak, which is kind of like the root of this hash basically. Then from that you have like a bunch of individual scripts, right? But then within those scripts we can then also have like this Taro commitment itself, right? And the top level, it has basically like a version. It has like some magic bytes so you can detect it easily. We need to do a bunch of things as far as to make sure their things can actually be unique as well too. And then you actually have the assets themselves. And there's 2 layers of trees. Once again, this is an SMT, so you can view it as kind of like a Merkleized key value lookup store, right? The first level is basically the asset IDs, which is like, once again, like this is like Bflex or whatever else. The next level is then like the actual individual UTXOs, right? So once again, you have like UTXOs that are sort of like, deferred in a sense because it's the same like a Bitcoin, but actually there's another tree. And then that UTXO itself, the asset UTXO, we call it like a TLV, particular serialization format, then points to a previous witness, which is another asset, and that's how you verify things today, right? So let's say I was going to prove to you I have, something like USDC or something like that, in my Bitcoin output itself. I would show you this series of Merkle proofs from the very beginning beginning from that top level thing. Then you say, okay, well, everything checks out. Now you have that thing. We can move forward. We can actually have this work as is right now. One thing is if you look at the way the proofs work today, they're actually explicit proofs, right? So I need to basically show you what are 3 or 4 levels of Merkle tree inclusion proofs, right? Which gets kind of large, particularly once you have either a bunch of assets or a bunch of things in the transaction level itself. So the goal is to say, okay, well, can we actually compress that stuff down basically together into something that's a little bit more smaller and doesn't actually need to grow over time? Because one of the things with this, and I think it's in the other slides, that over time, because you actually need to add a new asset every single time you're doing transactions, this file starts to basically grow over time, right? The thing is, it's not going to be larger than the actual Bitcoin blockchain because this is basically a subset of the transaction graph in the Bitcoin blockchain, but maybe some uses will actually be prohibitive because this thing starts to get a little bit too large. And this is basically what proofs look like today. This is like, the Taro, code. This is basically someone like decoding a proof. And you can see this is some of the information I talked about just now, as far as the asset, the name of the asset, the inclusion proof in the Merkle tree itself, and then also the SMT inclusion proofs. We also need to do exclusion proofs on the top level because, for example, we need to make sure that you're not cloning an asset in a transaction itself. The way we do that, we say, okay, well, give me an exclusion proof that either this thing cannot commit to an asset because it actually needs to be paid to a taproot. We also have a canonical commitment group within the TapScript tree itself, or it does, commit to assets, but not that particular asset that you need as well. That's why you also need the inclusion proofs. And this is basically what a proof looks like today. Like I was saying, it's basically just using inclusion and exclusion proofs and can get kind of large, in this setting once you have a lot of assets or a lot of coins, then you also need to repeat this every single time you're doing a new state transition as well. But as I mentioned, this actually has some issues as far as scalability, right? Because, if you're looking at something like a collectible, you basically just doing 1-to-1 every single time. And over time, the proof size basically starts to grow linear with the number of transactions that you actually have, right? So it starts out fine in the beginning. Maybe it's like a few hundred bytes, a few kilobytes, megabytes. Once you get into gigabytes, then it starts to get a little bit prohibitive as well, right? And the other thing as well, collectibles are a little bit easier because you can actually just do those linearly because you can't actually split them. It's always kind of like a 1-to-1 thing. But over time, once you have something like normal assets, you then also have inputs and outputs in the settings, similar to Bitcoin itself, right? So let's say I have 2 inputs. Well, I inherit basically the history of those 2 inputs as well too, and then that goes into the Genesis, the Genesis asset, similar to Genesis block, so that can get large over time, right? But the one thing at least is that in this setting, because all of them are coming from the actual same common ancestor, there is some redundancy in the proofs you can actually reduce over time to make things a little bit better. And as I mentioned a little bit earlier, this is still bounded by the actual growth of the Bitcoin chain itself, because this is a subset of the transaction graph, so it's not going to grow bigger than Bitcoin. And I think today maybe the graph is 480 gigabytes or so, including some of the major indexes as well, right? So that's one thing here. And one of the things you can do over time is sort of a way of doing probabilistic validation, right? So or verification. So basically imagine I had all these state transitions where we keep these proof files and I have a Merkle root of that itself, right? Similar to something that I think we're I was talking about here. You can then do samples. So, okay, rather than me verify these 1,000 state transitions, maybe I'll do 10 or so or something like that, and I'll do kind of a random sampling system to basically have some sort of standard boundness where I can say, okay, well this thing is fine because I verified enough of them. It's a legit asset. Let me move on and put my time elsewhere, right? Another thing you can do, you can actually use another level, basically a level of the inputs, right? So imagine if rather than Bitcoin actually having explicit inputs, basically input 1, 2, 3, 4, basically had a commitment to all the inputs themselves, right? Now that you have a commitment to the input, and also that commitment in the input is also a Merkle sum commitment, so it commits over the sum of all the input values within the system itself. So you can easily verify the input commitment and the output commitment verify the same value, but then you can then say, okay, well, rather than verifying all the inputs, I'll just do one level here and do the sampling and challenge game again, and then keep going like that as well. So that's kind of some short-term things, or mid to long-term things that the protocol run into. Some ways you can get around that, using various tricks. And so here we are, ZK Taro. Why do we actually care about this thing? Well, the main thing is basically using recursive Starks to actually reduce the proof size to what's effectively something that's more constant and more available to being distributed and actually used properly, right? So you can say there's kind of 2 levels of state transition function. One is basically saying, okay, well, the previous asset applied to a new witness gives you the new asset, but then once you repeat that over and over again, you have all the assets in the tree. Then you go on to the level and you say, okay, well, here's the previous Taro root and the new Taro root basically, and that leads to this new root basically. And you want to say, okay, everything else has been done properly, right? And one of the things here is kind of 2 layers in the proof itself. The first layer is, okay, well, let me prove that this structure commit was actually included in my TapScript tree, in the output, in the Merkle tree itself, and then in the header, and so forth. And that basically says, okay, well, this thing exists. Then the other thing is basically to verify that, okay, well, the state transition was done properly, which is basically saying that there's valid asset witness that if you have these particular rules, lets you kind of actually do the spend properly, right? The other thing as well is then you can actually then do that layer for the prior input. So imagine you basically have the initial proof, or you can you would go backwards or forward, but this is example of backwards. You have the initial proof. You say, okay, well, all this stuff is valid. Then I'll do that for the prior one and verify the prior one and so forth, basically, right? And this thing then, the end result is actually a single proof, basically, which is the asset itself. The proof basically states that, there is a transaction on chain that was, created and has an ancestor from this particular transaction, which actually created the asset itself. You have a series of transactions and transfers, and all this follows used properly. Now you have a niche state transition, which is say, okay, boom, this is my asset, and that's how you're going to go forward. So now we're getting to kind of like the bulk of it, which is like, okay, well, exactly how would that actually look like in a concrete fashion, right? So I think I have like, three sort of different design sketches. First, basically, okay, we'll have kind of like, first-class Stark primitives, right? So as I mentioned a little bit earlier, like, you do have to prove some attributes of Bitcoin within this proof itself. You need to prove, the header, the Merkle tree, the transaction itself, the TypeScript tree and things like that as well. So we can't actually change that, but what if we can focus on what we can change, right? Which is sort of like this commitment. So the commitment has some magic of version and a tree, right? But let's say we actually have a different version in the future. That tree can actually use, more Stark-friendly cryptographic primitives, right? Rather than use something like SHA-2, it can use like, Poseidon, tip5, rescue hash, whatever else, and like do things that are a little bit more, approvable within Starkland, rather than like actually inheriting everything else that we have alongside of it itself too, which is really cool. The other thing is, well, like, you don't necessarily need to like keep the TypeScript VM as we have right now. That could just be the arbitrary, Cairo programs, basically, based on the program hash, and then a series of public inputs as well too, right? And the cool thing about this, you can actually then still retain all the other aspects of the system as far as like, the amounts, the tag field, things like that as well too. But some of those can be all or some, be zero knowledge, or maybe you just really care about the computation and integrity part of it to basically show the thing has been moving forward and everything has been done properly, right? And then in this case, the witness now is that, okay, well, everything else was done, prior, in the past done correctly, but then also this new state is also done correctly as now as well too. And you can view like, you can say in Bitcoin, you can say the public input is basically just the public key. Let's say you do something like, public key opt text basically, and that's how it is right now. That'd be a similar thing, but then you also want to like also specify, okay, well, where am I setting the coin to the asset to? And in this case, that's also then that's going to be something that's going to be output from the program itself, as a kind of program output, which is then the public inputs. That's one way. This basically saying, okay, well, fuck it, we don't need to like, deal with anything else from the Bitcoin layer below. That can all just be redesigned to basically be a lot more friendly to the proof system itself, and maybe that's a little bit further off, but that's one way you can do it at least. Now, there's another way is, okay, well, let's say, okay, well, Taro itself is still a new system, right? It's not done. We're still evolving. We're still trying to make sure what's actually happening. We're not really, there's not like a final version. It's also not a mainnet yet, so I'm testing it right now. It's going to be mainnet this year. This is, okay, well, let's just keep everything exactly as it is. Still a young protocol. We're still doing everything right now. We're actually just like doing Stark proofs on top of the existing proof format itself, right? So what this means is that like rather than like saying, okay, well, we're going to redesign the entire commitment, we're actually just going to prove what we would execute anyway, in the Stark itself. And I mentioned a little bit earlier, so the way it works is like, the actual scripting system within the Taro VM is actually an instance of the Taproot VM, which is TapScript itself, right? So this would mean like, once again, actually implementing, Bitcoin script itself in Cairo, and then rather than like just saying, okay, well, this is some other arbitrary program, we're actually proving proper execution of what would be a Bitcoin script itself, right? And the way the Bitcoin script works, you can say that like, a program, is satisfied with passes the final execution if there's a single element on the stack left, and that element is 1, 0, 1. So we say, okay, well, we have the Taproot key, which is like this top level thing. There exists a TypeScript commitment in that key, which if you apply the witness to, would lead you to empty stack, so a final stack state of 0, 1, and also this new Taproot key as well too. And this is something that's, really cool. And like I mentioned, we have this project called Zero Sync. Just it has all the primitives. It has like ECSA, has SHA-2, has RIPMD, all of them has on Cairo, but doesn't really have, all of the, all of the existing Bitcoin VM, and also all the new software since 2013 as well too, right? And something like this, you would eventually also want kind of like, Cairo built-ins for performance purposes as well too, right? Because, you're going to be doing a lot of hashing. You have, these different signature operations as well too. And, there's probably also some challenges around kind of like, representing like the stack structure in the immutable environment, but I know that people have a bunch of like, different things in Cairo 1 and better syntax sugar to basically hide some of the immutability from the actual programmer itself. That's one. Basically, okay, let's keep it as is. We'll just like run ZK Taro in parallel with the normal Taro as well. Everything still works. Everything is still great. Oh, I don't know if I mentioned it earlier, but you can actually send these assets over Lightning, which is a really cool part. You can get like a low cost payment channel network part of it as well too. And then this is like another version. You can say, well, let's just kind of like, add structures in Cairo is basically like a new Taro VM version within the system itself, right? So I mentioned a little earlier, there's a few different like, versioning systems. Today we have like a script version, like what's kind of like a script key, which is basically governed by the script version itself. Today, version 0 basically says, okay, well, apply the TypeScript VM root to Taro itself. What we do is we basically take that kind of like, Taro station system, then basically map onto like a virtual Bitcoin transaction that has like an input and an output, which isn't really real, but we can actually reuse all the, functionality of the Bitcoin environment. So, okay, we're going to validate this as though it was something like this itself, right? And the cool thing, we can say, okay, well, TypeScript has something called the leaf version. So in addition to basically the top level version on like the op1, op2, which is basically StarkWare version, there's also a leaf version, meaning that every single leaf also has a version that can say, okay, well, I can use that to actually add additional functionality to Bitcoin itself. But in this case, we're actually in Taro land, right? So let's say we add a new, leaf version that says, okay, leaf version, OX, Z or OXOD, I think CD is the current one, something like that. This basically then can now allow us to actually sort of like, test run what would be a eventual, software for something like Starks, but actually in Taro land itself, right? So we can say, hypothetically, we can create some sort of like, op-Stark verify type opcode, right? And this opcode would basically be fashioned as though it was actually in Bitcoin itself, because it's actually in the same environment itself. But then we actually now are able to like, settle out the constraints of the current system as far as like not being able to pop from the stack. People know familiar with kind of like the way, software work on Bitcoin itself. And the cool thing here is then you can say, okay, well, we now are able to have this verification system work, but the verifier doesn't actually need to know about the conditions of what it's proving, or sorry, it's being verified. It can only need to know the public hash as well as the public inputs as well too. And then in Bitcoin, there's something called like an annex. Some people some people think it shouldn't be used, and maybe think it's broken, like somewhat undefined basically. But the idea was, okay, like let's say you're adding something like Starks in Bitcoin itself. The way Bitcoin works right now, you have something called like a SIGOP cost. You can say, okay, well, every single block can have a certain amount of bytes, a certain amount of SIGOP cost within itself, and you say every single signature is 50 SIGOP, something like that, right? But then the question, okay, well, how do you price the resource consumption of something like a Stark proof itself, right? So the idea was, okay, well, you can actually, you would put this thing in the annex, you can actually statically pop that thing off and examine it basically, and then compute some sort of like resource graph function that maybe is a function of the actual proof size rather than the trace length there. That can be used potentially. So, okay, well, how do you actually have this thing, work, but not, maybe, consume all the Bitcoin blocks and all the state within itself, right? And this is like one way you can do it as well. You can even do it in a way that, allows aggregation across like a, several block itself, something similar to the Schnorr signatures, half aggregation. Future directions: contribute to zero-sync development, get more Bitcoin script validation in there, do soft work stuff, get the inclusion proofs in there, investigate, Cairo built-ins to accelerate these things as far as like, SHA-2s, like P operations, things like that as well too. Then start to implement the Cairo primitives within Cairo itself, ASA TLV, SMT, serialization, things like that as well too. Another cool thing with this, like if you assume you have something like this, you can actually then do, ZK, sort of like bridging between, Taro and other systems as well too. For example, maybe someone has something like USDC, they want to like have a proof to basically suspend that thing, and then you basically verify them on the Taro layer and do the other way around as well too. And yeah, any questions? I think I have time for questions. Cool. Thank you. Yeah. Yeah, I had 20 minutes. I see what I did.
What is the advantage or disadvantage of using UTXO with while working on this type of?
The advantage of using UTXOs versus like accounts, the account model. I think the UTXO like has some advantages in that like it's parallelizable because you already have explicit sort of like dependencies in the chain, right? Like transaction A explicitly depends on transaction B or something like that. So you don't actually have like a shared state, so therefore you can validate things a lot more easily. I think the other thing as well is that like you have a lot less storage, right? Because in this case the storage is basically just the output scripts themselves, right? The output scripts can then commit to other things that you can then reveal at you can say transaction time itself. So you don't need to deal with basically having all the storage, and things are a lot more parallelizable. And I think also the application model is a lot easier to analyze because you don't really have arbitrary like calling of other contract rates. So you can basically look at the actual thing itself, and depending on how you do the constraints, things are just a lot more constrained, therefore it's easier to analyze, and then you have parallelizability gains and understandability gains as well. Yeah.
So for the verified use case, for allowing like VMs to track each other, do you have any thoughts on in Taro, where is data, how does data go to Taro?
Good question. Yeah, so like it's not actually an op return. I don't know if I can go back, maybe not. But like with the way it works, like you have a commitment basically, and the commitment is to that particular asset TLV, and that data doesn't actually live on chain. That like lives in what we call like sort of like universe servers, which themselves are this sort of like series of trees that commit to they basically use the previous out point as like a key in a Merkle tree itself, right? So for example, let's say I have a transaction, I can look at the previous out point, in that key, basically input being spent. I can say, okay, well, this is the actual data that I can use to validate. So the data, you can say the data is actually stored mainly entirely off chain. With the incentive there is okay, in order to actually transact with your asset itself, people need that data to be available in order to verify it themselves. If they can't actually if they can't obtain the data, then they can't use the asset, they can't verify it itself. So this kind of like it's like an off-chain system that you commit to everything on chain. They look at Bitcoin-like, but then you would fetch the data from elsewhere. For example, like, let's say you had an asset, I want to interact with it. I first need to fetch that initial proof, the genesis proof, and say, okay, well, this thing was created, has these particular rules, and I can go forth and verify everything else.
I see how that can work for UTXO applications where the use case is payments. So like each UTXO, you own each UTXO is owned by one person. But how about like for applications like DeFi where you have like shared state and like it's not, you might like I think it doesn't do that shared state, but not.
Yeah, good question. I mean, so I mentioned a little bit earlier, like you don't have the shared state, but you can kind of like have dependencies referencing your transaction, right? So your transaction would depend on maybe transaction 1 and 2 and 3 basically, and you would need those together in order to be validated, right? And there's some people that have ideas where it's like, right now you basically have the UTXO set, which is, keyed according to the output, which is the TXID and the output itself. Maybe you may need also another index that's basically based on like the script itself, right? Because otherwise, the issue is right now that like you can only spend a UTXO one time in a block. So if you have several transactions maybe depending on that same contract, the same script, they can't really reference each other, right? But you have some other identifier, which would be another index within the system itself. You can say, okay, well, these three are actually referencing this particular script. We can bundle them together basically, so now we have that dependency recomputed and execute them all at once. Any other questions? Cool. Great. Thanks so much.